In your Algebra 2 classes or in your pre-calculus classes, you may get systems of equations where you have 3 equations and 3 unknowns. And these are a little bit difficult to solve because you have to eliminate a lot of the variables at once, and it becomes a mess, and lots of times you make errors. Well, what I'm going to present today is a systematic way of solving 3 by 3 equations. They'll work for larger systems of equations also, but we're going to look at a 3 by 3. So here's a 3 by 3 system. 3x plus y minus 2z is equal to 2. X minus 2y plus z is equal to 3. And 2x minus y minus 3z is equal to 3. And so in a lot of cases you try to multiply one row by another row and subtract and try to eliminate those particular y variables or z variables or x variables and narrow it down to just one variable. So the method I'm going to show you today is the same idea, except we're going to use matrices and eliminate all of those variables from the pictures. So what I've done here is I've taken the system above and I've put it into 2 matrices, a square matrix on the left and a column matrix on the right. So you see that the coefficients of the x, y's, and z's are in that square matrix, and the what I call the answers are on the right-hand column matrix. Okay, the strategy to do this is going to be the same for any 3 by 3 that you encounter. First is you have to diagonalize the square matrix, and what that means is we turn everything into a 0 except for the diagonals, and those are going to be turned into 1s. And as we do that, it's going to change the column matrix on the right. So more specifically, we're going to turn that into a 0, that into a 0, that into a 0, and we're going to do it in that order. That's kind of important. Next, we're going to turn that into a 0, that into a 0, and finally that into a 0. Now, as we're doing all of that, the diagonal terms will be turning into 1s, and we will make decisions on how to do that as we go along. And if we do it correctly, then the elements in the column matrix will turn into the answers to the problem. It's a pretty cool result. Okay, so let's see how we do that. First off, there are 3 rules you have to follow. Here they are. The first thing is we can swap any 2 of the rows. Now what that means is that a particular horizontal row of the square matrix and along with it the element in the column matrix can be swapped with those in another row. And the right way I've written that is r sub I interchange with r sub j. So you simply swap the rows. For instance, if you swapped rows 1 and 2, you would do that in the square matrix and also correspondingly in the column matrix. The second rule says r sub I is replaced by alpha times r sub I. What that means is we're going to multiply each element of a row by some non-zero constant. And if you think about it, you've been doing that all along throughout your algebra career, and that is, if you have an equation, you can multiply one side of the equation as long as you multiply the other side of the equation by some value, some non-zero value. And then the third rule is replace a row by the sum of itself and a constant multiple of another row of the matrix. And the way I've written that is r sub I is replaced by r sub I plus some alpha, again a non-zero constant, times r sub j. Okay, so this one we'll see, it looks a little complicated, but we'll see that it's pretty straightforward. The only thing that's kind of tricky about it is that you have to do some thinking and looking at what the matrix is doing. So let's take a look. Okay, so here's our original matrix that we had earlier. First thing I'm going to do is I'm going to swap rows 1 and 2. Now you say, well, gee, why are you doing that? Well, if you notice, the first element in row 2 is a 1. And remember I said that we want to diagonalize this matrix by putting 1s along the diagonal. If we swap rows 1 and 2, that 1 will appear in its proper position in the first row and first column, or first position. Okay, so let's go ahead and do that. Okay, so we have swapped rows 1 and 2, and now we're one step closer to the overall solution. So we have the 1 in row 1, column 1. Okay, so what do we do next? So we want to turn in row 2, we want to turn that 3 into a 0. How do we do that? Well, if we use that third rule that I talked about, if we take the second row and we subtract from it row 1 multiplied by 3, it will be 3 times 1 minus 3 will give us a 0. And the way we write that is row 2 is replaced by row 2 minus 3 times row 1. Now, you may be thinking, well, what's going to happen to the rest of the columns in in row 2? Well, things will happen. In other words, we will multiply that -2 in row 1 by 3. We'll get a -6, and we'll subtract that from 1. So 1 minus a -6 will give us a 7, and that will appear in row 2, position 2, or column 2, if you want to talk about rows and columns. Likewise, in the third column of row 2, we'll say -2 minus 3 times 1 will give us -2 minus 3, or -5. Okay, so we'll have a -5 there. And if you're thinking that it's getting worse and worse, it's really not. Actually, things will look like they're getting worse, but as we go along through this method, you'll see that things become better and better, closer to our solution. Okay, and now likewise, remember, we have to do everything all the way across and even into the column matrix. So we would say in the column matrix, the 2 minus 3 times the 3. And so that would give us, well, the -3 times 3 is -9, and you add that to the 2, and you'll get -7 in that second position of the column matrix. Okay, so let's try that and see what we get. And indeed, that's what we got. We got a 0, which is what we want, in the first position, and then the consequences of that are that you get a 7 in the second position, a -5 in the third position, and in the column matrix you get a -7. So let's forge ahead, because this system works. All right, so for the third row, we have a 2 sitting there in the first position. We want to turn that into a 0. So we take that and we subtract from it 2 times the first row. Okay, so that would look like this. R3 is replaced by R3 minus 2 times the first row. So all we're concerned about really is that first position. All of the other elements in that row will change into something else, and we'll deal with those as we go along. Okay, so when we do this, indeed, it becomes a 0, and the other elements have changed according to that rule that we had before. Okay, so what do we do next? you remember that we say, okay, we're going to go from the one we just did to the second position of the third row. So we're going to change that 3 into a 0. But before I do that, I'm going to do a little trick here that will initially look like it's making the problem twice as bad, but in essence it is actually going to make the problem much, much simpler. And that is, I'm going to divide the second row by 7 to turn that middle, or that second position 7, into a 1. And I'm going to divide the third row by a 3 to turn that second position into a 1. And that looks like this. Row 2 is replaced by row 2 divided by 7. Row 3 is replaced by row 3 divided by 3. And again, this is that second rule that we talked about. What you do to one side of an equation, you have to do to the other side of the equation, or basically just you can multiply through by any non-zero constant. Here we're actually dividing, or if you want to say, we're multiplying by the reciprocal. So I'm multiplying by 1/7 in the second row and multiplying by 1/3 in the third row. Okay, so when we do that, hold on to your hats, we get this. And we've got fractions coming up. Well, the fractions are for those of you who are afraid of fractions, don't be, because there's some interesting things that we can do with them. All right, so back to our strategy, that in the third row, that second position which says 1, we want to turn that into a 0. Well, the easiest way to do that is just simply subtract the second row from the third row, or R3 is replaced by R3 minus R2. And what that will do is that will change that second position of the third row into a 0. But then you're going to say, I know, you have to take -5/3 minus a -5/7. That means you're going to have to get common denominator, and the common denominator there I think is 21, but it can be done. So when you do it, this is what you get. And you're going to say, oh, this is looking more horrible, because we've got -20 over 21. And remember now that the idea for this whole process was to turn the diagonals into 1s. Well, ask yourself the question, what multiple can I do, or what can I multiply that third element by to make it 1? And the answer is, I multiply it by negative, the negative times the negative gives us a positive, reciprocal of 20 over 21, or 21 over 20. And that's exactly what I'm doing right here. So when you do that, you get 0, 0, 1 as our third row, and then the column matrix a 0. Now, you'll find out a little bit later that we now have the first answer. That is, we have the answer to what the third variable z is equal to. Z is equal to 0 in the final solution there. Okay, next, we want to change that -5/7 into a 0. And more importantly, we don't want to change any of the other values. So that third row becomes real important to us right now, because there are zeros in the first and second position. All right, so we're going to take the second row and replace it by 5/7 by itself plus 5/7 times the third row. And what you notice there is, since we have a 1 in the third position of the third row, that will simply be 5/7. We add 5/7 to -5/7, and we get 0. like that. And notice we now have the second solution, or the solution for the second variable, I should say. So we know now that not only is z equal to 0, but y is equal to -1. So the next step is in the first row, we want to get rid of that third value, 1, and simply what we'll do is we'll take the first row and subtract from it the third row. And so that does not change any of the other values, only that third position in the first row. So that looks like that. R1 is replaced by R1 minus R3. That does that. And now, see if you can think of the strategy of the final step. Okay, if you've given yourself a chance to think about that, what you do is you multiply the second row by 2 and add that to the first row. So R1 is replaced by R1 plus 2 times R2. And when you do that, the second position of the first row becomes a 0, because 2 plus -2 is 0. And then 2 times -1 is -2. Add that to the 3, and what would you get? That's right, the answer is 1. And so we now have the solution set for our problem. So there's our diagonal. Notice everything else is 0. And there are our answers. Now, remember that I said that when we got to that third row, I said that the answer for z was equal to 0. Now, let's look at each one individually, and notice that the meaning of these two matrices is as follows: 1x plus 0y plus 0z is equal to 1. And what that means is, since the y's and z's have zeros, that 1x is equal to 1, or x is equal to 1. Likewise, the second row says 0x plus 1y plus 0z is equal to -1. And of course, that means y is equal to -1. And then finally, 0x plus 0y plus 1z is equal to 0. As I had said before, that means that z is equal to 0. So now we have the solution. X comma y comma z is equal to 1 comma -1 comma 0. And oftentimes in your math classes, you will stop there and say that is the solution. But oftentimes the teacher does not say, what does that mean? And what that means, I have a picture here that I did with the nice website called GeoGebra. It's a 3D plotting app on a web page. And what this is this is the graph of those three original equations shown as flat planes in the three-dimensional space. And in this picture, the x-axis is the one which goes from left to right, and I've put an X there in yellow. The y-axis in this picture goes from outside of the page into the page and is there. The z-axis is perpendicular to both of those and goes up goes from down to up, and I've labeled it there with a red Z. So now these three planes that are plotted have an intersection point of 1, -1, 0, and can be seen right there. And if you look at the picture closely, you'll see that this indeed is what that means. If we go positive x on the positive x-axis 1 unit, and then go -1 on the y, which would be coming out of the page, and then don't go up or down any, that is indeed where this point lies. So that's the more physical meaning of what this three-dimensional solution is. So before I go, I want to give you one problem to try on your own. So here's a system of 3 equations and 3 unknowns. Okay, so take a moment and copy that down. 2x minus y plus z equals 7. X plus y minus z is equal to -4. X minus 4y plus 3z is equal to 18. So using the Gauss-Jordan elimination method that you saw in this video, try to do that on your own. Now I'll give you the solution to that, but go ahead and try it and see if you get this solution. If you do it correctly, your solution will be 1, -2, 3. So you can jot that down too. And you know, if you make a boo-boo on the problem, go back and find the errors and try to fix them. But that will be the solution that you should get. So if you do that, you'll get the correct solution. So I hope you have fun trying that. And the purpose of this video is really to tell you that doing 3x3 systems of equations doesn't have to be a mental nightmare. You can do it with a very systematic approach. So I hope you enjoyed that, and I'll see you next time.